So in the previous video, we saw hash tables and we started to talk about probability as a tool for analyzing hash tables, and we talked through probabilities and random variables. I want to just now continue by talking about the expected value of a random variable. So let's bring back our diagram where we have a sample space. This is a die rolling random variable. I've got my red stuff here denotes the random variable acting as a map, mapping the outcomes to numbers to real numbers. And then I've got my green arrows here that represent the other nature of the random variable, which is that it has a probability distribution that maps the outcomes onto probabilities. And so if we just ask a simple question, which is what's the value that we expect from a die roll, it's going to be, something like 3 or 4, right? Like one of the values in the middle. And in fact, we can define the expected value of a discrete random variable as basically its average value, average but weighted by the probabilities of the different values. Okay, so what do we mean by values? We mean these. We mean the numbers that the random variable, the real numbers that the random variable maps the outcomes onto. Right, so this definition of an expected value includes this word value, which refers to one nature of the random variable, which is that it maps outcomes onto real numbers, and these are the real numbers, these values, and the other nature, which is that it has a probability function, right? And so this is basically just a weighted average of the values weighted by the probability. So in this example, it's a simple example because it's a fair die. We're just going to add up 1/6 times each of the 6 values that we can get from the die roll. Okay, so 1/6 times 1 times 2, 3, 4, 5, 6. And I'm using color to show how these, the different components of these terms come from the two parts of the random variable, either the map or the probability function. Okay, so the expected value of a fair die rolling random variable would be 3.5. So in the mathematical definition of this weighted average would be to take the sum over all possible small x's of small x times probability that big X equals small x. And it's simply that weighted average that we already discussed. Maybe the only thing you have to think a little bit about is what are the small x's? What are the small x's that are being summed over? And the answer is, well, it's all possible outcomes of the experiment, or really I should say all possible real valued outcomes of the experiment. In other words, not the outcomes themselves, but the real number that they get mapped to. So in this, obviously in this example, the x would be 1, 2, 3, 4, 5, or 6. So with that definition, there's just one property that I want to be able to cover about the expected value of a random variable called linearity of expectation. It'll come up again and again and again. And it's a very convenient thing to know. It's also pretty easy to state. It's simple to state. And it's very freeing because once we can use linearity of expectation, it actually allows us to use random variables as long as it makes sense to consider the expectation, the expected value of those random variables. It lets us use them in a much more natural, we can use a greater breadth of algebra that we already know in order to manipulate these random variables. So let's say we have a collection of discrete random variables, x sub 1 up to x sub n. All right. What linearity of expectation says is that the expected value of a new random variable, which is simply the sum of all the random variables, so sum from I equals 1 up to n of x sub I, the expected value of that equals the sum I equals 1 up to n of the expected value of x sub I. So what happened there? I had one expected value over the entire larger random variable, which was the sum of all the constituent random variables. I have that on the left-hand side, but then on the right-hand side, what I've done is taken the expected value operation and pushed it into the summation, so that now I'm taking the sum of the expected values of each of the individual random variables. Okay? And this property holds regardless of whether those constituent random variables, all of the various x sub i's, regardless of whether they're independent. And we haven't defined independent yet, and we will define independence later, but intuitively speaking, what this means is that even if the outcome of one of the x sub i's depends on the outcome of another one of the x sub i's, even if that's true, it's still the case that linearity of expectation holds. Okay? So another way to sort of write to write down linearity of, or to think of linearity of expectation is in terms of what kind of algebra does it let us do if what we're dealing with is the expectation, the expected value of a random variable. All right, so here's an example where we're taking the expected value of a combination of two random variables, both multiplied by a coefficient. Let's say a and b are just constants. So constant a times random variable b plus constant b times random variable y plus constant c. What does that equal? Well, what linearity of expectation says is that we can take the expected value and sort of push it in to these products, and we can take the summation and pull it out, just like we did up here. Right? So this equals a times expected value of x plus b times expected value of y, and then plus c, because the expected value of a constant is just that constant. Right? It's sort of it's like the constant has probability 1, so the expected value of the constant just pushes the constant back out, and the constants can come out of the expected value. So this isn't expected value of a times x, this is a times expected value of x. We can always pull a constant coefficient out of an expected value. So we can do a lot of the things that we're used to doing with symbolic variables if what we have is the expected value of the random variable, rather than just the bare random variable itself. Okay? This is also reflected in the ease with which we can combine random variables, right? So if the way we want to combine them is we just need to combine them by their expected value, then it's usually much easier to do that than if we need to, for example, try to figure out what's the probability of a particular joint event happening between all those random variables. So let's just take an example. Let's say I define a random variable z, and it's just the sum of these three random variables where I've got two die rolling random variables, one coin flipping random variable. So let's say it's 1 for heads, 0 for tails. And so z is just nothing but a sum of constituent random variables, 3 of them. Okay, and so when we have a random variable that is a linear combination of others, like z is, then the expected value of that random variable can be easier to work with than the probability function. Right? The probability function for z, it's not too hard to figure out. Like, what's the probability, for example, what's the probability of w plus x plus y equals 10? Right? That's something that we could figure out when the two die rolls and the coin flip all add up to 10. You can figure it out. But so much easier is to say, for example, what's the expected value of that z random variable? Well, we can just take the expected values of the 3 constituent random variables. Those are all easy, right? The two die rolls are both 3.5, like we already saw. The coin flip's obviously 0.5. We just add them all together, we get a number, and that's always going to be easier for us to do. So this will recur because often when we are considering random variables that are modeling situations, for example, with hash tables or with Bloom filters or other data structures we'll talk about, if there's a way of describing that random variable as a linear combination of other random variables, and those random variables have simple expected values, then it's easy for us to then construct the expected value for the larger random variable. Okay, so let's bring this probability knowledge that we've just reviewed back to hash tables, and think about how we can apply them to hash tables, because, you know, like this diagram is sort of asking, what's the x? You know, if we want to ask questions about the hash table and how many elements are in how many items are in each bucket. So what's the capital X? What's the random variable? What's the probabilistic analysis we really want to do? And the answer is just, it depends, right? It'll be a different analysis for different situations, and we'll see some specific examples in a moment. But broadly speaking, we know that the scenario we want to be able to answer questions about is, I've added m items to an n bucket hash table, and now I want to characterize what I see in the hash table. We know that we therefore are going to define some random variables. Okay, so besides that setup, what else do we need in order to define the random variables describing the table? Well, broadly speaking, the table has a sample space, right? We need to define what's the sample space, omega. All right, so intuitively, it makes perfect sense that the sample space is going to have something to do with how the items have been allocated to the buckets. Like, it might be the set of all possible ways of allocating m items into n buckets. Okay? So we're going to need to define that, though, right? We need to define what is the sample space. So we'll do that, and we'll suggest one way we could define the sample space in a moment. We also need the probability function, right? So in this sample space, what's the probability of each possible configuration if the sample space is all possible configurations of the hash table? So we need that too. And then finally, we need the map from the outcomes to real numbers, right? Now, these last two things, the probability function and the map, and to some degree also the sample space, but mostly these second two, really depend on what's the question that we're trying to ask, and what are the assumptions that we're going to make about the hash function that's spreading the items out across the bins. So taking all this in mind, let's talk about one popular way of modeling and analyzing hash table-like scenarios, which is called balls and bins. And balls and bins is just a kind of visual metaphor for exactly what we're doing when we are hashing items into a hash table. But it uses the terminology of throwing balls into bins. So the idea is I throw m balls into n bins randomly, which is to say uniformly and independently. So uniformly means every ball has an equal chance of going into any bin. And then independently means whatever happens with one ball depends in no way on any of the other balls, right? Each ball has a separate, entirely new, uniform chance of ending up in any bin. And so if this is the scenario, if this is sort of our random model for what's going on with the hash table, well, first of all, this means that we're assuming that the hash function is going to have this uniform and independent assumption. It's going to satisfy this uniform and independent assumption. And we'll talk more about that later, because we kind of need to convince ourselves that that's true, or that it's true enough. But what's clear now is at least we know what the sample space is, right? We know that the sample space is all possible ways of throwing m balls into n bins. And what's visualized here concretely is the case where we have 2 balls and 3 bins. All right, so this is all possible ways of throwing 2 balls into 3 bins. Okay, so we're almost done. Let's go back to that list of questions that we said we might want to ask to analyze the state of the hash table after we've added m items to an n bucket hash table. And we wrote down these interesting questions, right, in contrast to the not so interesting questions that we tried to answer without probability. And I'm just going to replace all the mentions of items with balls and all the mentions of buckets with bins and make a new slide. So there you go. Highlighted in blue is all the changes that I had to make. But I think it's pretty clear that the questions being asked here correspond exactly to the questions we were asking before. We're just putting the model of the balls and bins on top of the hash table. Okay. Now let's think a bit more specifically about questions that we can ask and approaches, modeling approaches that we can take to answering those questions. Okay, so here's the overarching question. I throw m balls into n bins uniformly and independently. What are the sorts of questions I can now ask? And I've divided them into categories, and let's start with this first category of so-called empty, non-empty questions. So one empty, non-empty question might be, how many bins are empty? Question mark. And another question might be, and sort of empty, non-empty question is, what's the chance that all bins are non-empty? And for these sorts of empty, non-empty questions, we can use, it's still the balls and bins model, but we're now in a pretty specific special case of the balls and bins model. The special case where the question we're asking really only has to do with empty or non-empty. Doesn't have to do with how many things are in the bins necessarily, just whether it's greater than 0 or not. And for those sorts of questions, there's going to be a kind of canonical approach that we can apply called coupon collector, which we'll come back to when we discuss Bloom filters. Okay, so those are my empty, non-empty questions. The next type of question are questions that have to do with whether there were collisions or not. Collisions being two balls going to the same bin, two items going to the same bucket of the hash table. So what are some collisions, no collisions type questions? Well, how about like how many balls how many throws until there's a greater than 0.5 chance of a collision? Or what is the chance of no collisions? In other words, no more than one ball per bin. And so for questions like these, collision or no collision type questions, that's another special case of a type of question that we might ask. And they're going to be, they can be analyzed with another specific approach, which is the birthday problem. All right, which you may have heard of. It's usually discussed in probability classes. So birthday problem is another sort of special case that we can use. Another category are questions about how many items there are in a particular bin, in a single bin, right? Or how many items there are in a particular bucket of the hash table. And so these questions, obviously just what's the occupancy, the number of items in it, what's the occupancy of a given bin? And then another is what's, like, for example, now we can go to numbers besides 0 and 1, which is basically what coupon collector and birthday problem are allowing us to study. So like, what's the chance a given bin has more than 2 items? And so for these types of questions, we're generally going to use analysis of some kind of random variable that's just trying to model one bin. And so that might be a binomial, or it might be a Poisson random variable. In certain situations, it might be a geometric random variable. We'll have more to say about what those types of random variables are later on. But binomial, geometric, and Poisson random variables are very common ways of trying to analyze occupancies of bins or buckets. And then finally, we have global occupancy questions. So these are questions that have to do with how full the bins are, but not with respect to a specific bin, but sort of in a way that requires understanding the full distribution of bin occupancies. So for example, we can ask, what's the median number of balls in a bin? Or what's the maximum number of balls? And you might say, well, the maximum is always n, right? And that's true. But what's the maximum with high probability, right? Because it is, of course, possible for all m balls to go in the same bin, but for high enough m and n, you know, that's it's exceedingly rare. But so with high probability, we can usually bound what's the maximum number of balls per bin. And so what's the maximum? You know, we could ask with high probability or something like that. And these questions are harder, right? None of the special cases above are really helping us there, or at least not in full generality, right? I'm saying in general, we don't necessarily have a quick approach for answering those questions, though they all have, you know, they've all been analyzed and there's literature on what are the answers to many of these. For the purpose of this course, we're generally going to be sticking to the strategies up here: coupon collector, birthday problem, or random variables that we're using to model what's going on in a particular bin.